The ground at Norris Geyser Basin is too hot to walk on. Not metaphorically, not as a figure of speech. Literally, the soil temperature in a section of the basin that was open to visitors 18 months ago has exceeded the boiling point of water at Yellowstone's altitude. The boardwalks are closed. The signs say thermal disturbance. The scientists say something else entirely. They say the heat is coming from below, not from the hydrothermal system, not from the superheated water that has circulated through Yellowstone's plumbing for centuries. From below the hydrothermal system, from the layer beneath the layer that powers the geysers and the hot springs and Old Faithful itself. From the magma. In the 6 weeks since we covered the April 2026 anomalous data, the deep seismic swarm, the accelerating ground deformation, the new thermal feature at Norris, every single monitoring parameter the Yellowstone Volcano Observatory tracks has moved in the same direction, not back toward baseline forward. The helium-3 signal in the gasochemistry data came back elevated. That is the fingerprint of mantle-derived gas. That is the chemical signature of material that originated not in the hydrothermal system, not in the circulating groundwater that most Yellowstone activity comes from, but in the magmatic system, in the partially molten rock sitting 5 to 17 kilometers below the surface of Wyoming. The deformation rate at the Norris GPS cluster has not decelerated. It has increased to 3 centimeters of uplift recorded in the first 90 days of the episode has been followed by an additional 4.1 centimeters in the past 6 weeks. The rate is not dissipating. It is accelerating. The thermal anomaly at Norris, the 340-meter feature identified in the April satellite data, has expanded. The new measurement puts it at 510 meters in diameter. The temperature differential above background has increased from 2 degrees Celsius to 6.8 degrees. And 3 days ago, something happened at Norris that has not happened at any point in the modern monitoring era. A new fumarole opened. Not an expansion of an existing thermal feature. Not a change in an existing geyser or hot spring. A new opening in the ground, venting gas directly from a source that the observatory's geochemical team immediately sampled. The gas composition of that fumarole is not consistent with a shallow hydrothermal source. The sulfur dioxide concentration is 4 times what has been recorded from surface hydrothermal features at Norris previously. The carbon dioxide to sulfur dioxide ratio is within the range characteristic of direct magmatic degassing. The magma is communicating with the surface, not through kilometers of hydrothermal plumbing, directly, through a new crack in the crust above it, opened by the pressure building from below. That is what the instruments are showing tonight. That is what the scientists are looking at. And that is why the Yellowstone Volcano Observatory has, for the first time in its institutional history, raised the Yellowstone alert level from green to yellow, aviation color code yellow, ground alert advisory, using language in its official statement that includes a phrase it has never previously published in an advisory. Magmatic contribution to observed surface activity cannot be excluded. Cannot be excluded. That is the language of a scientific institution saying, in the most carefully calibrated words available to it, that what is happening at Yellowstone right now is no longer explained by the hydrothermal system alone. Tonight on Project Nightwatch, we are going to walk through every piece of that new data. We are going to explain what the alert level means and what it doesn't. We are going to tell you exactly what the next escalation looks like, what the scientists are watching for, and what the range of outcomes, from the probable to the historically precedented to the genuinely catastrophic, actually is. We do not do panic here. We do not do dismissal. We do the work. Hit like and subscribe if you're here for the truth, exactly as the instruments are recording it. Tell me in the comments where you're watching from tonight. And tell me this, when a government agency uses the phrase, cannot be excluded about magma at Yellowstone, do you think they're being honest enough? Drop that in the comments. The United States Geological Survey uses a 4-color alert system for volcanic hazards: green, yellow, orange, red. Most people who follow Yellowstone know that the alert level has been green, the lowest category, for the entirety of the modern monitoring era. It has never been raised, not during the 2007-2008 uplift episode, not during the 2003 Norris thermal disturbance, not during any of the significant unrest episodes that have occurred since systematic monitoring began, until 3 days ago. The current level is yellow. Before we talk about what that means, let me be precise about what it does not mean. Yellow does not mean eruption is imminent. Yellow does not mean evacuation is being considered. Yellow does not mean the worst-case scenario has become the most likely scenario. What yellow means, in the USGS's own formal definition, is this: a volcano is exhibiting signs of elevated unrest above known background levels, or, after a change from a higher level, that volcanic activity has decreased significantly, but continues to be closely monitored for possible renewed increase. elevated unrest above known background levels. The key phrase there is known background levels. The observatory has 40 years of systematic monitoring data for Yellowstone. It has established what background looks like across every parameter it tracks. It knows what normal deep seismicity rates look like. It knows what normal deformation rates look like. It knows what normal gas chemistry ratios look like. What the instruments are showing right now is not normal. It is not within the range of variation that characterizes the monitoring record. It is above it, and moving further above it rather than returning toward it. That is what justified the alert level change. Not a single dramatic event, not a precursory explosion, not a visible surface eruption. The slow, sustained, multi-parameter departure from everything the monitoring network has established as background behavior. The alert system exists for exactly this situation. For the moment when the accumulating evidence across independent monitoring streams reaches a threshold that formal institutional language is required to communicate. That threshold has been crossed. And the question that every volcanologist in the United States is asking right now, the question the data is forcing onto the table, whether the scientific community is ready to answer it or not, is which direction the system moves from here. Yellow is not the end of the scale. It is the second rung of a four-rung ladder. The rungs above it have names. And understanding what those names mean, what data would justify moving to them, is the only way to understand what we are actually watching. Was the April anomaly the beginning of a sequence that is now escalating? Or is yellow the ceiling, the point at which the system stabilizes and begins its long return to baseline? The instruments will tell us, and tonight, we start reading them. When we covered the April anomaly 6 weeks ago, one of the key pieces of data we said to watch for was the helium isotope ratio from the gas chemistry sampling that had been intensified at Norris Basin. That data is in. Helium comes in two stable isotopes, helium-3 and helium-4. The ratio between them, written as He, is one of the most diagnostic tools available in volcanology for tracing the origin of volcanic gases. Here is why. Helium-3 is primordial. It was produced in the first 3 minutes after the Big Bang, incorporated into the material that eventually formed the Earth, and has been slowly outgassing from the planet's interior ever since. The mantle is rich in helium-3. The crust is not. As primordial helium-3 is released from the mantle, it rises. As it moves through the crust toward the surface, it mixes with crustal helium-4. Produced continuously by the radioactive decay of uranium and thorium in continental rocks. The ratio of helium-3 to helium-4 therefore tells you where a gas sample came from. A high ratio, close to the mantle value, means the gas originated deep in mantle-derived material. A low ratio, close to the crustal value, means the gas spent most of its journey in the crust, mixing with radiogenic helium-4, losing its mantle signature. At Yellowstone, the helium isotope ratios in hydrothermal gases have been measured for decades. The baseline ratio, the value changes to surrounding features and elevated ground temperatures. Steamboat entered a period of sporadic activity that continued through the 1970s and 1980s. In 2003, as mentioned in our previous coverage, Norris experienced the most significant thermal disturbance recorded in the modern monitoring era. A zone of the Tantalus Creek area registered ground temperatures high enough to melt road asphalt. Several new features appeared. Existing features changed character. The basin was partially closed to visitors. The disturbance resolved over approximately 8 months. In 2018, Steamboat Geyser entered a period of extraordinary activity, erupting 32 times that year after having been essentially dormant for 3 years. Scientists linked the activity to a hydrothermal disturbance in the Norris area that was accompanied by elevated seismicity and minor ground deformation. The episode resolved by 2021 as Steamboat's eruption frequency declined. Each of these episodes, and there are others in the record, represents a period when the Norris Basin was expressing elevated heat and fluid flux from below. Each of them resolved, none of them escalated to eruptive activity, but each of them was driven primarily by hydrothermal processes, changes in the circulation of superheated water through the existing plumbing system, changes in flow paths, pressure, and heat distribution within a system fundamentally driven by groundwater interacting with a deep heat source. The current episode is different in a way that has not characterized any of those previous disturbances. The helium signal is different. The 14.3 raw ratio does not appear in the records of previous Norris disturbances. The gas chemistry from the 2003 episode, the most severe in the modern monitoring era, remained consistent with hydrothermal sources throughout the disturbance. The depth of the seismicity is different. Previous Norris disturbances produced seismicity concentrated in the 2 to 8 kilometer range, the hydrothermal zone. The current swarm's deep component at 12 to 20 kilometers places it below the hydrothermal system entirely and within the zone of the magmatic reservoir. The focal mechanisms are different. The tensile failure signature in the deep events has not been reported in the analysis of previous Norris swarms. The current episode shares the surface expression of previous Norris disturbances. Elevated temperatures, new features, ground uplift. But the subsurface signals driving those surface expressions are qualitatively different from what has driven them before. That difference is what the alert level change is communicating. It is not communicating that Yellowstone is about to erupt. It is communicating that what is happening right now at Norris is not the same as what happened in 2003 or 2018 or any of the previous historical episodes. Something new is happening. And in a system as consequential as Yellowstone, new is a word that demands full attention. One of the most fundamental characteristics of the Yellowstone caldera is that it breathes. This is not a metaphor. The caldera floor literally rises and falls over years-long cycles, driven by the movement of hydrothermal fluids and, in some episodes, as we have discussed, by pulses of heat or material from the magmatic system. Between 1923 and 1984, the period for which the earliest reliable deformation records exist, the caldera floor rose approximately 85 centimeters. From 1984 to 1995, it subsided approximately 22 centimeters. From 1995 to 2000, it rose again. The cycle is continued, breathing in and out, on timescales of years to decades. This cycle is the system's way of accommodating the continuous inflow of heat and material from the mantle plume. Below, the episodic pressurization of the hydrothermal system and the slow but unceasing creep of tectonic loading. In normal breathing, in the caldera's baseline behavior, the deformation pattern is broad and smooth. The entire caldera participates in the inflation and deflation. The GPS stations spread across the park all move in roughly the same direction at roughly the same time. The pattern looks like a balloon being inflated and deflated, a distributed, symmetric response to a distributed, deep pressure source. The current deformation pattern does not look like a balloon. It looks like a blister. The uplift is concentrated at Norris. It is not caldera-wide. The GPS stations outside the Norris area, the ones positioned in the center and southern portions of the caldera, are showing minimal motion. The Norris cluster is rising at approximately 3.4 centimeters per month. The other stations are showing a few millimeters at most. A blister, not a balloon. A localized, asymmetric inflation centered on a specific zone, directly above the deepest seismicity, directly above the tensile failure events, directly above the new fumarole. This pattern is telling the scientists something that the older, distributed episodes did not tell them. The pressure source is not the main magma reservoir, the large deep body distributed across the entire caldera. The pressure source is localized. It is beneath Norris specifically, and it is at a depth that, combined with the seismic and geochemical data, points to something that is not simply the hydrothermal system responding to a deep heat pulse. A localized pressure source at magmatic depth beneath the most geologically vulnerable surface point in the entire caldera, producing tensile fracturing in the overlying rock, with gas chemistry indicating direct magmatic contribution, and a surface uplift pattern that is accelerating rather than decelerating. That is the physical picture the data is painting. It is not a picture of an eruption, but it is a picture of a system moving in a direction, and the direction it is moving is upward. There is a detail in the most recent observatory field report that did not appear in the headline summary, but that volcanologist reading the full document paused at. A section of the Grand Loop Road, the main tourist route that passes through the Norris area, has developed a series of surface cracks over the past 3 weeks. The cracks are linear, oriented roughly northwest-southeast, and extend over a distance of approximately 400 meters along the road margin. They are not large. The widest is approximately 4 centimeters across, and the deepest measured is approximately 30 centimeters. The Park Service has marked them and is monitoring them. The field report's interpretation: thermally induced surface, cracking consistent with differential ground expansion, associated with elevated near-surface heat flux. In plain language, the ground is cracking because it is getting hotter from below. Surface cracking in thermally active areas is not unusual at Yellowstone. The 2003 disturbance produced similar features in the Norris area. The cracks are not a sign of imminent collapse. They are not precursors to a specific eruptive event, but they are a physical manifestation of the same process producing every other signal we have discussed tonight. The ground is rising because something below it is pushing upward, and as it rises and expands, it cracks. The road is cracking because the earth beneath it is expanding, and the earth beneath it is expanding because something below the hydrothermal system, something at magmatic depth, is pressurizing. The road doesn't lie. The GPS doesn't lie. The helium doesn't lie. The seismicity doesn't lie. Every independent measurement system is producing data that points in the same direction. The question is whether that direction is a dead end, a magmatic system testing a pathway, finding it insufficient, cooling back into the crust, or the beginning of a road that has a surface expression at the other end. Let's talk about sulfur dioxide. SO2, sulfur dioxide, is one of the primary gases emitted by magmatic systems. Unlike carbon dioxide, which can originate from both magmatic and crustal sources, sulfur dioxide in significant concentrations is almost exclusively magmatic in origin. Crustal rocks and hydrothermal fluids do not generate large sulfur dioxide fluxes, magma does. The baseline sulfur dioxide emission from Yellowstone, measured continuously by an instrument network at the surface, is approximately 40 to 75 tons per day. That is actually relatively low for a system sitting above an active magmatic source, and reflects the fact that most of the magmatic gas at Yellowstone is scrubbed by the enormous hydrothermal system before it reaches the surface. The hydrothermal fluids absorb the sulfur dioxide, converting it to sulfate that ends up dissolved in the water. The current measurement from the Norris fumarole area, taken over the past 72 hours using direct flux measurement, 340 tons per day localized to the Norris Basin alone. 340 tons per day from one area of one geyser basin, more than the previous total emission for the entire Yellowstone system. That number is not consistent with a hydrothermal source. The hydrothermal system does not produce 340 tons of sulfur dioxide per day. That number is consistent with a direct magmatic source, with gas exsolving from melt and finding a pathway to the surface without being fully scrubbed by the overlying water system. It means the pathway between the magmatic source and the surface is not just more permeable than before. It is sufficiently open that the scrubbing capacity of the hydrothermal system, the enormous buffering effect of millions of liters of circulating groundwater that normally absorbs magmatic gases, is being overwhelmed in the Norris area. More gas is coming up than the water can absorb. That is a fundamentally different statement about the state of the system than anything in the monitoring record. To put 340 tons per day in context, Mount St. Helens in the months before its 1980 eruption was emitting approximately 200 tons of sulfur dioxide per day. Pinatubo, in the weeks before its catastrophic 1991 eruption, was emitting 5,000 tons per day. The current Norris emissions during the 40 years of systematic monitoring. The 640 0-year gap is relevant for a different reason than the overdue narrative. It is relevant because it tells us something about the current state of the magmatic system after 640,000 years without a super eruption. The shallow magma reservoir is in a specific state. It has been accumulating heat and volatile pressure from the mantle plume for that entire period. It has been cycling through uplift and subsidence episodes, pressurizing, then partially releasing, then repressurizing. Each of those episodes has been resolved by one of two mechanisms. Either the pressure dissipated back into the system, or it was released through smaller eruptive events, lava flows, hydrothermal explosions. The system has not had a major pressure release in at least 70,000 years, the age of the last significant lava flow eruption. 640,000 years of input with only partial outputs. The pressure budget of the system is not zero. The volatile content of the melt is not empty. The system has been loading. What the current data might be showing is that after a period of loading that has no modern precedent in the monitoring record, the system has begun to express that loading in a new way, not through the hydrothermal system. That valve has been open for 640,000 years and has not been sufficient to fully decompress the magmatic source. Through a new pathway, through the fractured zone above the magma reservoir at Norris, where the crust is thinnest, where the plumbing is most direct, through the crack in the road, through the new fumarole, through the helium-3 in the gas, through the centimeters of rising ground. The magma is not at the surface, but the pressure from the magma has found a new way to speak, and it is speaking in a language the monitoring network has not heard before. Alert level orange at Yellowstone would represent the most significant formal volcanic hazard designation in American history. No volcano in the contiguous United States has been at orange for longer than a few months. In those instances, Mount St. Helens, in the periods leading to its 2004-2008 dome-building eruption, involved a system with a very different geometry and a much shallower magmatic source. Orange means eruption is considered foreseeable if trends continue. It means that the monitoring data has crossed multiple thresholds. It means that the probability of eruptive activity in the near term is considered significant enough that formal emergency management protocols are activated. For Yellowstone specifically, an orange designation would trigger a cascade of formal responses. The National Park Service would begin evacuation of the park. At peak season, Yellowstone hosts approximately 30,000 visitors per day. An ordered evacuation of the park could be accomplished in approximately 8 to 12 hours under good conditions, the surrounding gateway communities, West Yellowstone, Gardner, Cook City, Jackson, would be included in the evacuation advisory. FEMA would activate pre-positioned response assets for the broader Yellowstone region. The FAA would impose flight restrictions over the caldera area, consistent with the Aviation Color Code Orange designation that accompanies the ground alert. The NRC, the Nuclear Regulatory Commission, would conduct precautionary assessments of the potential impact of elevated seismicity on nuclear facilities within a 1,000-kilometer radius. None of these responses have been activated. None of them are imminent based on the current yellow designation. But they exist, they are planned, they have been rehearsed, and the fact that they are planned tells you something important about how seriously the relevant agencies take the low probability, high consequence end of the Yellowstone's risk distribution. The gap between yellow and orange is defined by the three thresholds I described earlier. The current data is below all three thresholds. For orange to be declared, the monitoring network would need to show one or more of sustained caldera-wide deformation approaching 10 centimeters per month, sustained shallow seismicity above magnitude 3 for more than 72 hours, or a system-wide sulfur dioxide flux approaching 1,000 tons per day. Those are not trivial thresholds. They represent a substantial escalation above current conditions. But they are thresholds that the current trajectory of the data could reach in weeks to months if the acceleration continues. Not certainly, not probably, but within the physical range of what the current system state could produce. That is the honest assessment. That is what yellow, combined with an accelerating multi-parameter data trend, actually communicates. Most Yellowstone coverage focuses on the geological drama, the super eruption numbers, the cubic kilometers, the global temperature effects. What it rarely focuses on is the immediate human geography. The population that would be in the path of even a non-super eruptive Yellowstone event in the early stages of a developing crisis. Let me give you the numbers. Yellowstone National Park receives approximately 4 million visitors per year. Peak daily visitation in summer months reaches 30,000 to 35,000 people within the park boundaries. The gateway communities surrounding the park, West Yellowstone, Gardner, Cook City in Montana, Jackson and Cody in Wyoming, have a combined permanent population of approximately 25,000, with summer seasonal populations 2 to 3 times higher. Bozeman, Montana, the nearest city of significant size, is approximately 145 kilometers from the Norris Basin. Its metropolitan population is approximately 120,000. Idaho Falls, Idaho, approximately 200 kilometers from Norris, has a metropolitan population of approximately 145,000. Casper, Wyoming is approximately 350 kilometers away. For a hydrothermal explosion scenario at Norris, the most probable significant near-term eruptive scenario, the immediate lethal zone would be within approximately 5 to 10 kilometers of the event. The secondary hazard zone from pyroclastic surge would extend to perhaps 15 to 20 kilometers. This is entirely within the park boundaries for an explosion of the scale the current data could potentially support. The ash fall from even a relatively small explosive event at Norris, a hydrothermal explosion producing a column that reaches 15 to 20 kilometer altitude, would deposit ash across a downwind area of hundreds of kilometers. The prevailing winds across Yellowstone are westerly, meaning ashfall would affect Wyoming, Montana, the Dakotas, and potentially further east. Ashfall of even a few millimeters is sufficient to ground aviation, clog vehicle engines, contaminate water supplies, and damage crops. For the affected region, the immediate priorities in the early stages of any eruptive event, before the scale of the event is fully characterized, would be evacuations of the park and surrounding communities, closure of airspace, and the activation of the monitoring to response chain that the USGS has spent decades designing. The 30,000 to 35,000 people in the park on any given summer day are not at risk from the current yellow alert. The park remains open. The observatory's assessment does not support closure, but those 30,000 people are inside a national park that sits above a supervolcanic system that has just raised its alert level for the first time in its monitoring history. They are visiting a geological wonder that is right now expressing itself in ways it has not expressed in the 40 years of systematic monitoring. They are walking boardwalks above ground that is cracking from thermal expansion. They are photographing fumaroles that are venting gas with a mantle signature. They deserve to know what the instruments are showing, not so they panic, not so they leave in a rush that creates its own hazards, but because information is the only tool that allows human beings to make rational decisions in the face of geological uncertainty. The park is open, but it is open above a system that is not behaving the way it was behaving a year ago. In 2011, a paper was published in the Journal of Volcanology and Geothermal Research by a team of researchers at the University of Utah and the Eskies. The paper was titled, in the careful language of peer-reviewed science, something along the lines of Seismic Evidence for Partial Melt Migration Beneath the Norris Geyser Basin, Yellowstone Caldera. The paper argued, based on a detailed reanalysis of seismic velocity data from the monitoring network, that there was a zone of anomalously low seismic velocity in the crust directly beneath the Norris Basin, at depths between 8 and 14 kilometers. Low seismic velocity is a signature of hot, partially molten material. The authors interpreted this zone as a region where melt from the shallow magma reservoir had migrated into a previously unmapped pocket of partial melt closer to the surface than the main reservoir, a magmatic outpost, as it were, extending the reach of the magmatic system upward beneath Norris. The paper received modest attention at the time. It was cited in subsequent tomography studies. Its implications were discussed in the volcanological community, but it was not widely treated as a finding that changed the understanding of near-term Yellowstone hazard. Because in 2011, the surface data at Norris was not showing any of the signals that are showing now. 13 years later, those signals have arrived, and the zone of low seismic velocity that the 2011 paper identified, the partial melt pocket at 8 to 14 kilometers depth, sits directly within the depth range of the tensile failure events in the April swarm. It sits directly below the accelerating surface deformation. It sits directly below the new fumarole. The paper was describing what was already there. The current data is describing what that pre-existing feature is now doing. The scientists who wrote that paper were right. The partial melt is there. It was always there. What is new is not its existence. What is new is its behavior. Something has changed in the magmatic system that is causing that pocket of partial melt to interact more actively with the overlying crust than it has in the monitoring period. The pressure from below, from the main magma reservoir, and from the mantle plume beneath it, has changed in a way that is pushing the Norris partial melt zone into a more active state. The observatory is now conducting an updated seismic tomography analysis using the April swarm data to produce a new higher resolution image of the crustal structure beneath Norris.